Beneath a sky of sulfuric acid and an atmosphere dense enough to crush a submarine, NASA sent 4 probes into the clouds of Venus. All 4 of them broke at the same altitude. And for 15 years, nobody could explain why. This is mission data, transmitted back to Earth by the Pioneer Venus probes as they fell through the hottest, most violent atmosphere in the solar system. Then, decades later, scientists found Venus is not dead. In 1978, NASA launched Pioneer Venus, and it consisted of 2 separate spacecraft. One was an orbiter, designed to circle the planet and map its surface with radar. The other was a multi-probe bus, a carrier vehicle that would release 4 separate entry probes into the Venusian atmosphere. All 4 probes entered the atmosphere on December 9, 1978. They were spaced across different locations on the planet at different latitudes on both the day and night sides. By dropping probes at different points, scientists could build a 3-dimensional picture of the atmosphere. What was happening in the clouds above the equator compared to the poles? What was different between the sunlit side and the dark side? The design was elegant. The probes were enclosed in spherical titanium pressure vessels built to withstand the immense forces of the deep atmosphere. Instruments that needed direct contact with the outside air were mounted externally on booms and sensor boxes. Internal instruments, protected inside the sealed vessels, viewed the atmosphere through small windows. Everything was working. The probes transmitted data continuously during descent. Temperature readings climbed steadily as the probes sank deeper. Pressure built as expected. Cloud layers were mapped in extraordinary detail. 3 distinct cloud layers were identified, each with different particle sizes and compositions. Particle sizes were measured. Radiation was tracked. Wind speeds were derived from the Doppler shifts in the radio signals. The Pioneer Venus mission was being recognized as one of the most successful atmospheric science campaigns ever conducted. The data flowing back to Earth painted a picture of Venus that was both fascinating and terrifying. The sulfuric acid clouds extended from about 45 to nearly 70 kilometers altitude. Below the clouds, the atmosphere cleared into a dense, transparent haze. Temperatures climbed relentlessly. At 30 kilometers, it was already hot enough to bake bread. At 20 kilometers, metals like tin and lead would begin to soften. And the probes just kept falling, working exactly as they were designed to. And then they reached 12.5 kilometers. Here is where it gets strange. At an altitude of 12.5 kilometers above the surface, the external instruments on all 4 probes began to fail. Temperatures between 627 and 640 Kelvin, pressures between 36 and 40 bars. The temperature sensors, which had been tracking the rising heat with precision, suddenly showed a nearly discontinuous drop. The readings plunged far below the actual atmospheric temperature. On the large probe, the drop happened in approximately 2 seconds. On the smaller probes, it happened within 16 seconds. Both independent temperature channels on each probe, including one that was electrically insulated from the atmosphere, were affected simultaneously. The net flux radiometers on the 3 small probes showed equally bizarre behavior. The measured radiation dropped to essentially 0 within a few data samples. At the same time, the radiometer temperature sensors departed from their expected readings, spiking steeply upward to apparent saturation levels. On the night probe, the temperature reading first plunged to 350 Kelvin, then shot up to saturation. These events occurred within about 100 seconds of the temperature sensor failures. But here is the really strange part. The instruments inside the sealed pressure vessels continued to work perfectly. The optical radiation sensors, the cloud detection instruments, the mass spectrometer, all of them kept delivering valid data below 12.5 kilometers, all the way down to touchdown. Whatever was happening, it was only affecting the instruments that were exposed to the outside atmosphere. There were other anomalies too. On all 3 small probes, the status signals from the sensor deployment mechanisms suddenly indicated that the instrument booms had been restored, which was physically impossible. Cold junction thermistors on the small probes dropped to incredibly low readings, like 194 Kelvin, before recovering. On the large probe, thermocouple wires that had been deliberately cut before the heat shield was jettisoned began producing small voltage signals. The large probe bus current dropped sharply at 11.5 kilometers. It was a cascade of failures, and none of them made sense. Think about this for a moment. 4 separate probes, entering the atmosphere at different locations on the planet, on different sides of the world, carrying instruments built by different teams, all experienced the same type of failure at the same altitude. Whatever was causing this was not random. It was not a one-off glitch. It was systematic. Something about the conditions at 12.5 kilometers was fundamentally hostile to the way these instruments were built. The Pioneer Venus probe mission had been widely recognized in the atmospheric science community, highly successful and productive. It had established a new level of knowledge of the upper, middle, and lower atmospheres of Venus, replacing uncertain knowledge or speculation with actual measurements and observations. Major advances had been made in understanding the thermal structure and stability of the atmosphere, cloud altitudes, particle densities and sizes, atmospheric composition, horizontal winds and vertical velocities, the detection of wave systems, and the balance of solar and thermal radiation. But the data from below 12.5 kilometers was compromised. Valuable science from the deepest part of the atmosphere was lost, and the implications were serious. If future Venus missions were to carry external sensors into the deep atmosphere, they needed to know what had gone wrong. In the year after the encounter, limited investigations were conducted at Hughes Aircraft Company, the contractor that built the probes. No cause for the anomalies was identified. NASA sponsored a theoretical study at San Jose State University, which focused on sulfuric acid corrosion of the platinum temperature sensors. The predictions of that study were not entirely consistent with the observations and could not explain the simultaneous failure of the net flux radiometers. And then, for years, no further concerted attention was given to explaining what happened. This is the part of the story that often gets lost. The Pioneer Venus probes had delivered extraordinary science. They had established a new level of knowledge about the upper, middle, and lower atmospheres of Venus, replacing speculation with actual measurements in areas like thermal structure, cloud composition, wind patterns, and radiation balance. But the data from the lowest 12 kilometers was compromised, and nobody knew why. Scientists proposed several theories. Some suggested that the descending probes had become electrostatically charged while passing through the sulfuric acid clouds, and that the accumulated charge had triggered electrical discharges in the deep atmosphere, like lightning strikes on the instruments. Calculations showed that charged aerosol particles in the Venusian clouds could indeed charge the probes to very high voltages, potentially exceeding 500,000 volts. As the probes descended below the cloud layer, there were not enough ions in the atmosphere to neutralize the charge quickly enough. And, at around 12 kilometers, the atmosphere might reach a critical pressure where its resistance to electrical breakdown drops sharply. Energetic sparks could have occurred at the external sensors, which were the sharpest protrusions on the spacecraft, and therefore the most likely locations for discharge. Others considered the possibility that a conductive material, perhaps a metal, was condensing on the sensors in the deep atmosphere. There were tantalizing clues. The Magellan orbiter, which mapped Venus with radar in the early 1990s, had detected sharply lower radar emissivity on mountain surfaces above about 5 kilometers. The highlands were highly radar reflective, as if coated with something conductive. Some researchers speculated that a substance vaporized from the hot lowlands was condensing on the cooler mountain tops. If the same process was happening on the probes, a thin film of conductive material could short-circuit the sensors. Mercury was one candidate. It had been predicted to exist as a vapor in the deep atmosphere. But the mass spectrometer on the large probe placed an upper limit of 5 parts per million on mercury concentration, which was far too low to explain condensation at 12 kilometers. Potassium and cadmium were also considered. But equilibrium chemistry calculations showed that these metals would react with the atmospheric gases and form solid non-conductive compounds long before reaching the sensors. And then there was the most dramatic theory of titanium. The metal used to build the probe pressure vessels and structural components can be ignited in pure carbon dioxide at high temperatures. Equilibrium calculations confirmed that metallic titanium would burn in the deep Venusian atmosphere if its protective oxide layer were breached. Some researchers proposed that electrical sparks had ignited small fires on the probe's titanium components, which then damaged the instrument wiring. Each of these theories was interesting. None of them was conclusive, and so the mystery lingered. Part of the problem was that the probes had never been tested under realistic conditions. By project and contractor decision, tests simultaneously simulating the pressures and temperatures of the Venus deep atmosphere were not performed on the complete probes or temperature sensors. There was no equipment to reproduce Venus surface conditions. Building such test facilities was recognized to be costly and dangerous, requiring a large chamber heated to around 500 degrees Celsius at over 1,000 pounds per square inch of internal pressure. The program was run under tight budget and schedule constraints, much like modern Discovery-class missions. Some components were tested at high pressure, but not high temperature. Others at high temperature, but not high pressure. The full combination was never attempted. The pre-flight cable tests were performed in nitrogen at temperatures up to 760 Kelvin and pressures up to 100 bars. Because of practical difficulties achieving the desired pressure and temperature from bottled carbon dioxide, nitrogen was used instead. Both gases were considered chemically inert, so the substitution was thought to be satisfactory. But later analysis suggested that this assumption may not have been entirely safe. Equilibrium chemical calculations showed that carbon dioxide at 40 bars and 640 Kelvin is, for some substances, an oxidizing agent. It can oxidize titanium. It may also degrade organic polymers, like kapton, by oxidizing the hydrogen atoms in their molecular chains. In other words, kapton might burn in carbon dioxide at high pressure and temperature. None of this was tested before the probes flew. Now, there is an important detail that makes the Pioneer Venus anomalies even more puzzling. The Soviet Union also sent probes to Venus. Many of them, the Venera and Vega landers, descended through the same atmosphere, endured the same temperatures and pressures, and successfully transmitted data from the surface. Their external sensors, including temperature instruments, continued to function below 12 kilometers. Soviet Venera and Vega scientists were specifically asked whether any anomalous behavior occurred at 12 kilometers altitude. Their reply was that there was none. The Venera landers were built differently. Their central pressure vessels were titanium spheres, about 82 centimeters in diameter, encased in 11 centimeters of exterior insulation. The landing gear consisted of a toroidal shock-absorbing ring supported by tubular struts made of asbestos textilite, a fiber-reinforced polymer. Numerous external instruments were attached to this structure, but the critical difference may have been in the design details of the wiring and insulation. It is not clear whether the Soviet probes had exposed wire harnesses outside their pressure vessels, or whether these were protected within conduit. Whatever the difference was, it pointed to something specific about the Pioneer Venus probe design, not something about the atmosphere itself. This was a crucial clue. If the Venusian atmosphere at 12 kilometers were inherently hostile to electronics in some exotic way, the Soviet probes should have experienced problems too. The fact that they did not meant the answer had to lie somewhere in the engineering. in the specific materials and construction choices that made Pioneer Venus different from its Soviet counterparts. But identifying exactly what that difference was would take another 15 years, and the assembly of some of the brightest minds in atmospheric science and spacecraft engineering. In September 1993, 15 years after the probes reached Venus, NASA convened a workshop at Ames Research Center in California to finally resolve the mystery. The workshop brought together an extraordinary group. Probe system engineers from Hughes Aircraft Company, some of them now retired, project office personnel, instrument designers, atmospheric scientists, chemists, dynamicists, and electrodynamicists. The convener was Alvin Seif, one of the original investigators. The agenda was methodical. First, a critical review of every anomaly, both from the experiments and the spacecraft. Then, a presentation and evaluation of candidate hardware explanations. Then, the same for candidate atmospheric phenomena. Sub-panel meetings and discussions were used to work toward conclusions. The engineering panel found something that had been overlooked for 15 years. Almost all of the reported anomalies could be explained by a single mechanism: a breakdown of the electrical insulation in the external wiring harness that connected the sensors to the probe electronics. The external cables on the Pioneer Venus probes consisted of bare wire leads covered with woven quartz or glass fiber sleeves wrapped individually in Kapton, a polyimide film considered to be one of the best high-temperature polymer insulators available. The leads were lashed together into cable bundles. In some cases, pairs of Kapton-wrapped leads were enclosed in a braided metal shield that was also wrapped in Kapton. But here is the critical detail. At the points where the sensors connected to the harness, called field joints, the connections were covered with kynar shrink tubing. Kynar is a fluorinated hydrocarbon polymer known as polyvinylidene fluoride, and kynar decomposes at temperatures above 600 Kelvin. The manufacturer's own literature stated that the polymer unzips at those temperatures. When it does, it releases hydrogen fluoride, one of the most corrosive gases known. Hydrogen fluoride attacks glass, etches metal, and destroys organic polymers. In a confined space like a cable bundle wrapped in braided shielding, the gas has nowhere to go. It concentrates, reacts with everything around it, and leaves behind conductive residues. The probes reached 600 Kelvin at approximately 12.5 kilometers altitude. So here was the sequence. As each probe descended and the temperature climbed past 600 Kelvin, the kynar shrink tubing at every external field joint began to decompose. It released hydrogen fluoride gas into the cable bundles. The gas attacked the Kapton wrapping, the fiberglass insulation sleeves, and the wire itself. Conductive breakdown products, including carbon-rich ash from the decomposed polymer, infiltrated the insulation and created electrical pathways between conductors that were supposed to be isolated. The insulation resistance, which should have been in the millions of ohms, dropped to the low thousands. At that point, signals from the temperature sensors, the radiometers, the deployment switches, and the thermistors all became corrupted. Not because Venus was doing something exotic to the instruments, but because the wires connecting those instruments to the probe electronics were shorting out from the inside. All 4 probes experienced this at the same altitude because all 4 probes reached the same critical temperature at roughly the same point in their descent. The physics was identical, the failure was identical, and the explanation, once finally discovered, was devastatingly simple. After the workshop, the recommended harness tests were started at Hughes Aircraft Company under the direction of Victor Rogers. The test facility was a small chamber, about 7.5 centimeters in inside diameter and 23 centimeters long, capable of duplicating Venus surface temperature and pressure with either carbon dioxide or nitrogen. Specimens tested included harness material samples, harness specimens from modern jet engines, and samples of harness cut from a damaged Pioneer Venus temperature sensor. The samples incorporated field joints of the same type used during probe assembly. The results were definitive. Preliminary tests showed that Kapton, the main wrapping material, was not severely degraded in carbon dioxide at 655 Kelvin and 55 bars for more than 30 minutes. Kapton was not the problem. But when the Kynar shrink tubing was tested, it was reduced to a blackened ash at temperatures above 600 Kelvin. A pungent gas was present in the chamber after the test, which was later confirmed to be hydrogen fluoride. In tests of both the jet engine harness and the Pioneer Venus harness, both including Kynar shrink tubing over field joints, the insulation between the central conductors and the shielding dropped from more than 100 megohms to less than half a megohm at temperatures just above 600 Kelvin. The insulation remained low for 2 to 3 minutes, then partially recovered. This behavior was strikingly similar to what had been observed at 12 kilometers on Venus in the Pioneer Venus temperature data. After the tests, the breakdown voltage of the joints was unacceptably low, around 250 volts, versus the thousands of volts expected for proper operation. The Kapton film used to wrap the leads was charred in tests where Kynar degradation had occurred, probably because the released hydrogen fluoride attacked it. The stainless steel walls of the test chamber were discolored and pitted. A white crystalline residue was deposited on the walls, and when mixed with water, it was acidic enough to etch aluminum. The highly corrosive hydrogen fluoride gas released from the decomposing Kynar would have easily penetrated the braided metal shielding and the woven fiberglass insulation within the field joints, attacking the materials and leaving conductive deposits. The high carbon content ash from the decomposed polymer could also have infiltrated the fiberglass and contributed to the loss of insulation resistance. And here is the final piece of the puzzle. A search through old records revealed that Kynar shrink tubing was not in the original joint specification at the time of the final design review in June 1976. It was added later, possibly during final integration on the factory floor, when engineers encountered difficulties dressing the joints because of poor accessibility. Brief high-temperature tests were conducted to qualify the material, but those tests were done in nitrogen, not carbon dioxide, and at atmospheric pressure. The full simulation of Venus conditions, simultaneously high temperature and high pressure in a carbon dioxide atmosphere, was never performed on the complete cable assemblies. The probes were never tested under the actual conditions they would face at 12.5 kilometers. This is the lesson that reverberates through the entire story. The Pioneer Venus mission was run under budget and schedule constraints similar to modern Discovery-class missions. Corners were not deliberately cut, but certain combinations of conditions were never simulated because the facilities to do so were too expensive, too dangerous, or too time-consuming to build. A chamber heated to 500 degrees Celsius at 1,500 pounds per square inch of internal pressure is not trivial to construct or operate safely. And so, the decision was made to test components separately, at high pressure in one facility and high temperature in another, and to trust that the combination would not introduce new failure modes. That trust was misplaced. The Kynar shrink tubing had been qualified with brief high-temperature tests. Those tests showed that the material degraded, but was said not to impair insulation resistance. What those tests did not reveal was that the degradation products themselves, specifically the hydrogen fluoride gas, were the true threat. In the confined geometry of a cable bundle at high pressure, the released acid gas had nowhere to dissipate. It concentrated in the fiberglass insulation, attacked the wire coatings, and created conductive pathways between leads that should have been isolated from each other. The insulation resistance dropped from hundreds of megohms to kiloohm levels, more than enough to corrupt every external measurement on the probe. the Pioneer Venus anomaly was eventually solved. It was a hardware failure, not an alien signal, not an atmospheric mystery. But the story of what NASA found on Venus does not end there, because the planet had been hiding something far more profound, and it took another 30 years of staring at old data before anyone noticed. From 1990 to 1992, NASA's Magellan spacecraft orbited Venus and mapped 98% of the planet's surface using synthetic aperture radar. The radar signals penetrated the thick cloud cover, bounced off the rocky surface, and returned to the spacecraft carrying detailed information about the terrain below. The images Magellan produced remain the most detailed views of Venus we have to this day. Magellan revealed a world dominated by volcanic features, vast lava plains, shield volcanoes, lava channels thousands of kilometers long. The number of impact craters on the surface indicated a mean age of only a few 100 million years, far younger than the surfaces of the Moon or Mars. Many of those craters appeared to have been modified by volcanic processes, suggesting the average surface age might be only tens of millions of years, as young as Earth's ocean basins. Magellan imaged the surface over 3 orbital cycles, referred to as cycles 1, 2, and 3. During the first cycle, about 84% of the planet was observed with radar images looking to the east. During the second cycle, gaps were filled, and about 35% of the planet received a second set of images, this time looking from the west. A third cycle covered about 15%. In total, about 42% of the global surface area was imaged 2 or more times. These repeat observations were taken at different angles and separated by about 8 months. The different imaging geometries used for each cycle made automated comparison extremely difficult. The same feature could look dramatically different when viewed from opposite directions. This meant that any search for surface changes had to be done manually by human eyes comparing grainy, low-resolution images side by side. But here is the question that haunted planetary scientists for decades. Were those volcanoes still active, or had Venus gone geologically quiet? The answer was hiding in Magellan's own data. It just took 200 hours of manual searching to find it. Robert Herrick, a research professor at the University of Alaska Fairbanks, began systematically comparing Magellan radar images taken at different times during the mission. Because Magellan imaged the surface over 3 orbital cycles, some regions were photographed 2 or 3 times, with gaps of about 8 months between images. The different imaging geometries used for each cycle made automated comparison nearly impossible. So Herrick did it by hand, frame by frame. In a region called Atla Regio, a vast highland area near the equator that hosts 2 of the planet's largest volcanoes, Mons and Maat Mons, Herrick found something extraordinary. A volcanic vent associated with Maat Mons had changed shape between February and October 1991. In the February image, the vent appeared nearly circular, covering an area of about 2.2 square kilometers, with steep interior sides and signs of drained lava on its exterior slopes. In the image taken 8 months later, the same vent had nearly doubled in size and become irregularly shaped. It also appeared to be filled nearly to its rim, consistent with a lava lake having formed inside. Herrick teamed up with Scott Hensley at JPL. They built computer models of the vent in various configurations and tested different scenarios, including landslides. They varied the depth, the wall, steepness, and the terrain slope. They simulated how each version of the vent would appear under the 2 different radar viewing angles. Only a couple of the simulations matched what was actually observed, and the most likely scenario was that volcanic activity had occurred on the surface of Venus during the Magellan mission. The lava flows, visible in the second set of images, covered an area of about 69 square kilometers, consistent with typical hotspot volcanism on Earth. For comparison, the 2018 Kilauea eruption in Hawaii covered about 35 square kilometers. The associated caldera collapse at the summit of Kilauea had an area of about 5 square kilometers. This was the first direct evidence of active volcanism on Venus. Published in the journal Science in 2023, it confirmed what many had suspected but nobody had been able to prove. Venus is not a dead world. It is alive. In 2024, the story deepened. Scientists in Italy, led by Davide Sulcanese of D'Annunzio University, analyzed more archival data from Magellan. This time, they focused on radar backscatter, the strength of the signals reflected from the surface. By comparing backscatter data from 1990 and 1992, they found changes at 2 additional locations. The first was Mons, a volcano in a region called Isla Reggio. The second was in the western part of Niobe Planitia, an area filled with volcanic features. At both sites, the radar signal strength had increased along certain paths between the 2 observation periods. These changes were consistent with the formation of new rock, most likely solidified lava from eruptions that occurred while Magellan was in orbit. The researchers considered other explanations, including wind-blown microdunes and atmospheric interference, but the evidence pointed firmly to new lava flows. They analyzed Magellan's altimetry data to trace the topographic slopes and identify obstacles that flowing lava would have deviated around. The patterns matched what you would expect from a fluid moving downhill. Using terrestrial lava flows as a comparison, they estimated the new rock at both locations to be between 3 and 20 meters deep on average. The Mons eruption produced about 30 square kilometers of new rock. The Niobe Planitia eruption produced about 45 square kilometers. For scale, the 2018 eruption of Kilauea in Hawaii covered about 35 square kilometers. The 2022 eruption of Mauna Loa, Earth's largest active volcano, produced enough material to fill around 100,000 Olympic-sized swimming pools. The Venus eruptions were in the same ballpark. Venus does not have plate tectonics. There are no mid-ocean ridges, no subduction zones, and yet it has volcanic activity that may be comparable to Earth's hotspot volcanism. There are several dozen volcanoes on Venus, with sizes and gravity signatures suggesting they sit above hot mantle plumes larger than the one beneath Hawaii. Some models predict that multiple eruptions might occur over the course of a single Venusian sidereal day, which is 243 Earth days. If that is correct, Venus is not just geologically active, it is vigorously so. Now, there is one more anomaly on Venus that still does not have a proven explanation, and it connects back to the Pioneer Venus story in a way that is almost poetic. When Magellan mapped the planet, its microwave radiometer detected something unusual about the Venusian highlands. At elevations above about 5 kilometers, the surface showed sharply lower radar emissivity and increased conductivity. The mountaintops were highly radar reflective, behaving as if they were coated with something that conducts electricity. There is no confirmed explanation for this. But one leading hypothesis is that a volatile substance is being vaporized from the hot lowlands, transported upward by atmospheric circulation, and then condensing on the cooler mountain surfaces, much like frost forming on a cold window. The identity of that substance remains debated. Remember the Pioneer Venus probes? When scientists were investigating the 12.5-kilometer anomaly, one of the theories they explored was that a conductive material might be condensing on the probe sensors in the deep atmosphere. They noted that the Magellan radar reflectivity data was consistent with a substance that condenses at altitude on both the mountaintops and on objects slightly cooler than the surrounding air, like a descending probe. The insulation failure of the Kynar shrink tubing turned out to be the true cause of the probe anomalies. But the question of what is coating the Venusian highlands remains open. And the deeper question of what is happening in the lowest 12 kilometers of that atmosphere, in that thick, superheated, high-pressure layer where convection stirs material upward from the volcanic surface, is still not fully answered. We have studied less than 2% of Venus's surface in enough detail to detect volcanic changes. The search that found the Maat Mons eruption examined only about 1.5% of the planet. There could be dozens of active volcanoes on Venus right now, erupting beneath those opaque clouds, reshaping a surface that we last saw in detail more than 30 years ago. The atmospheric temperature data from Pioneer Venus indicated that the layer between 13 and 20 kilometers is stable, meaning air does not rise or fall easily through it. But below 6 kilometers, data from the Soviet Vega 2 lander found the atmosphere to be unstable and convective. Hot gas rises from the volcanic surface, carrying whatever is being vented by those eruptions, and is trapped beneath the stable layer like smoke pooling against a ceiling. What is accumulating in that layer? What compounds are being cooked, concentrated, and circulated in the lowest slice of the Venusian atmosphere? We do not know. The Pioneer Venus probes lost their external sensors before they could measure it. And no mission since has returned to find out. NASA and the European Space Agency are preparing to go back. In 2021, NASA selected 2 new Venus missions under its Discovery program. VERITAS, which stands for Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy, will orbit the planet and create 3-dimensional global maps using state-of-the-art synthetic aperture radar. It will carry a near-infrared spectrometer to determine the composition of the surface and measure the planet's gravitational field to map its internal structure. DAVINCI, the Deep Atmosphere, Venus Investigation of Noble Gases, Chemistry, and Imaging mission, will send a probe into the atmosphere to directly sample and analyze the gases on the way down. ESA's EnVision mission, slated for launch in the early 2030s, will carry its own synthetic aperture radar, being developed at JPL, along with a spectrometer to study the surface. Both Hensley and Herrick are key members of the EnVision radar science team, ensuring continuity between what Magellan found and what the next generation of instruments will search for. Together, these missions will give us our first comprehensive look at Venus since Magellan. And the stakes are enormous, because Venus is not just a curiosity, it is a warning. It is a planet the same size as Earth, with the same ingredients that became a furnace. Understanding how that happened, what role volcanism plays in maintaining that state, and whether Venus was ever habitable, are among the most important questions in planetary science. Whereas Magellan's data was originally cumbersome to study, delivered on boxes of CDs compiled by NASA and sent through the mail, the data from VERITAS will be available online to the global science community. Researchers will be able to apply modern computational techniques, including machine learning, to analyze the planet's surface in ways that were impossible in the 1990s. What took Robert Herrick 200 hours of manual comparison could potentially be done in minutes. The Pioneer Venus probes gave us our first real look at the deep atmosphere. They descended through sulfuric acid clouds, through crushing pressures, through temperatures that would destroy most materials on Earth. They sent back data that transformed our understanding of the planet. And they failed, ultimately, because a small piece of plastic tubing was never tested under the conditions it would actually face. That is both the humbling truth and the beautiful paradox of space exploration. We build the most sophisticated machines humanity has ever created, send them hundreds of millions of kilometers across the void, and sometimes the thing that stops them is something no one thought to check. Venus is the closest planet to Earth, and we know almost nothing about it compared to Mars. We have driven robots across the Martian surface for decades. We have never successfully operated anything on Venus for more than about 2 hours. The surface is too hot, too pressurized, too corrosive. The clouds are opaque, The atmosphere is crushing. And beneath all of that, the planet is alive. Volcanoes are erupting. Lava is flowing. The surface is being remade. We found evidence of that activity, not through some cutting-edge telescope or a new space probe. We found it by going back to data that was sitting in boxes of CDs, collected by a spacecraft that launched in 1989 and was powered down in 1994. It took a researcher spending 200 hours manually comparing grainy radar images, frame by frame, to see something that had been there the whole time. 200 hours, staring at pixels, rotating views in his mind, comparing a circle that had become a kidney shape. That is how we discovered that Venus is volcanically alive. And then, a year later, Italian researchers found 2 more eruptions in the same dataset. 2 more volcanoes that had been active while Magellan was watching. The data had been available to the entire scientific community for over 30 years. It just needed someone to look closely enough. And the Pioneer Venus anomaly, the one that stumped NASA for 15 years, turned out to have nothing to do with alien atmospheres or exotic chemistry. It was a piece of shrink tubing that no one tested properly. A material that was added late in the build process because it solved an assembly problem on the factory floor. A shortcut that decomposed in the heat, released acid gas, and destroyed the very instruments it was supposed to protect. Sometimes, the biggest mysteries have the simplest answers. And sometimes those simple answers open the door to even bigger questions. We are going back to Venus. When we get there, we will see a surface that has been reshaping itself for the past 30 years, unobserved. We will peer through the clouds with instruments that are orders of magnitude more powerful than anything Magellan carried. And we will, for the first time, have the technology to ask Venus the questions that the Pioneer probes were never quite able to answer. What is happening beneath those clouds? What is being vented, heated, pressured, and transformed in that lowest layer of atmosphere where our instruments went dark? We do not know yet, and that is exactly why we are going back.